Today we're going to introduce and discuss exponential functions. So a basic format of an exponential function is you might have some type of constant, I'm calling that a, and this constant, it turns out, is always going to be the y-intercept. We'll see this in a future example, but we'll have some constant times another constant raised to a variable power. So the important thing to notice here is when you have an exponential function, the variable, the x, is part of the exponent. This number that I'm calling b is called the base of our exponential function. It's always going to be a positive number, and it won't equal 1. So let's start by trying to identify exponential functions. So I've got a list of 3 functions. Which of the following are exponential? The first one is not. This is actually a polynomial. Notice the exponent is a constant and the variable is the base. That's a polynomial. The second one, f of x equals 2 to the x, the base is a constant, the variable is the exponent, so yes, that is an exponential function. And then the last one, f of x equals 5 to the negative x plus 2. That is also an exponential function because that variable is in the exponent. So we've got 5 to the negative x plus 2. We'll see later on in this video that we can actually just think of that as an exponential function with a graphing transformation. All right, so let's practice writing exponential functions. Find an exponential function that contains the points 0, 4, so we actually know the y-intercept, and the point 2, 36. So we can start with the basic pattern. If we have an exponential function, it can be written of the form f of x equals a times b to the x. We know 2 points, and so we can actually plug these numbers into our function for x and for y. So this first point is telling us when x is 0, so you can put 0 in for x, the output, the y value is 4. And the second point is telling me when x is 2, the output, the y value is 36. So I have 2 equations. 4 equals a times b to the 0, and 36 equals a times b squared. 2 equations and 2 unknowns, this is something I can solve. And in fact, the equation I have on the left, 4 equals a times b to the 0, well, b to the 0, anything to the 0 power is always equal to 1. So that equation simplifies down to a equals 4. And I'm not surprised that I got a equals 4 because this constant a is always the y-intercept. Our y-intercept was 4, so a has to equal 4. We can use that information then to solve for b. So if 36 equals a times b squared, we can put the 4 in for a and then solve for b. If I divide both sides by 4, I get 9 equals b squared. Take the square root. B has to equal 3. The base of your exponential function is always going to be a positive number, so you don't have to worry about a possibility of negative 3. Exponential functions always have positive bases. So b equals 3, and my function is f of x equals 4 times 3 to the x. All right, let's do another example. This one, we don't know what the y-intercept is, and I think we're going to get numbers that aren't quite so nice. Let's see if we can find an exponential function that contains the points negative 2, 6, and 3, 1. So I'm going to start this the same way I did the previous problem. I know that an exponential function has to be of the form f of x equals a times b to the x. When x is negative 2, the output is 6. When x is 3, the output is 1. So I have two equations and two unknowns. To solve this, I'm going to pick one of the equations, and I'll start with the equation on the left. And I'm going to try to solve this equation for one letter, for one variable. To help me solve this equation, I know that when we have negative exponents, they actually mean reciprocals. So I can take this b to the negative 2 and move it to the bottom, and it becomes a b squared. So this first equation, 6 equals a times b to the negative 2, is equivalent to 6 equals a divided by b squared. We can solve this equation for a by multiplying both sides by b squared. The b squareds cancel out on the right. And now I'm left with a equals 6 times b squared. Now we can take this expression for a and plug it into my other equation. So I'm basically using a method of substitution to solve these equations. So I'm going to substitute into the second equation for a 6b squared. So now I have 1 equals 6b squared times b to the third. B squared times b to the third is b to the fifth. Add the exponents. And then to solve for b, I divide both sides by 6. So 1/6 equals b to the fifth. And then finally, I can take the fifth root. I know that b has to equal the fifth root of 1/6. Okay, so we're halfway there. We know what the b is. To figure out what the a is, I'm going to take this value, fifth root of 1/6. I'm going to plug it in for b in my equation that solved for a. So if a is 6b squared, that means a is 6 times fifth root of 1/6 squared. All right, we've solved for both a and b. Let's see if we can clean up these numbers a little bit. So let's see. A was 6b squared, so a is 6 times fifth root of 1/6 squared. The fifth root of 1/6, well, if you take a root of 1, you just get 1. So that's 1 over the fifth root of 6. And we can rewrite that fifth root as a 1/5 power. So this is the same as 1 over 6 to the 1/5. And if we square that, that becomes 1 squared is 1, over 6 to the 2/5. So a is going to be 6 times 1 over 6 to the 2/5. Technically, this is division. I have 6 divided by 6 to the 2/5. When we divide, we can subtract the exponents. 1 minus 2/5 is 3/5. So this simplifies down to a equals 6 to the 3/5. So a little bit cleaner, still not that nice of a number. But now we can write our exponential function. I'm going to change the b. I'm going to make that look a little bit nicer. b, we said earlier, fifth root of 1/6 is 1 over fifth root of 6. So we can write that as 1 over 6 to the 1/5, or 6 to the negative 1/5. So plugging that into my exponential function, f of x is a, so 6 to the 3/5, times b, 6 to the negative 1/5, raised to the x. And there's my exponential function. We could leave it like that. Or when we have parentheses, we can multiply the exponents. So we could write this as f of x equals 6 to the 3/5 times 6 to the negative x over 5. Now, if we have an exponential function whose base is bigger than 1, this is going to be exponential growth. This means the function values will be increasing. If that base is smaller than 1, the function values will be decreasing, and we can describe this as exponential decay. So here I have two different tables of values, and the question is, which of these is exponential growth? So in both of these tables, The y values are increasing. So they're both describing some type of growth. But when we have the exponential growth, if I go back a screen, when we have exponential growth, the values are increasing by some factor or some multiplier. So we might see y values that are doubling or tripling or growing by 20%. So they're growing by a common multiplier or a common factor. So back to these two tables. The one on the left, the y values go from 2 to 6, then 6 up to 18, and then 18 to 54. These values are actually tripling. To get to the next y value, you just multiply the previous by 3. They're growing by a factor of 3. Whereas the table on the right, the y values are increasing, but from 2 to 5, and then 5 to 8, and then 8 to 3, or 8 to 11. And in this case, the y values are going up by a fixed amount. We can add 3 to get to the next y value. The outputs are increasing by that fixed amount of 3. What this means is the table on the left is an example of exponential growth. The y values are growing by a factor. The table on the right is actually an example of linear growth. If we were to graph the one on the right, we would get a straight line with this constant slope or constant increase. So the table on the left is the one that's exponential growth. And I can actually write equations for both of these situations. For the table on the left, it's exponential growth, so it's going to fit into that pattern. F of x equals a times b to the x. The a is the y-intercept, or the initial value. We're starting at 2. And the b is actually that multiplier. These values are tripling, so the b is actually going to be 3. We can verify this by plugging numbers in. If you plug 1 in for x, 2 times 3 is 6. If you plug 2 in for x, 2 times 3 squared, 2 times 9, is 18. For the table on the right, this one is linear growth. The y-intercept is 2. That's my b, or my initial value. And the slope is 3. So we can write this as f of x equals 2 plus 3 times x. And again, you could check if you plug in 1 for x, 2 plus 3 is 5. If you plug in 2 for x, 2 plus 6 is 8, etc. Now, one specific example of exponential growth is compound interest. So I have a special kind of exponential function on the screen. This is our compound interest formula. The A, the output, stands for the future value of our account. How much money will we have in the future? The P, this is our y-intercept. This is our initial value, or sometimes called the principal. This is the amount you're starting with. The R is your annual growth rate. N is the number of times compounded per year. So if you have interest that's compounded or paid out annually, that means once per year, N would be 1. If you have interest that's compounded monthly, that means the interest is paid out monthly, and the N is 12. T stands for number of years, and then let's see, we already said A is future value. So let's see how this works with a specific example. $5,000 is placed into an account that is compounded monthly at 6% interest. So again, compounded monthly means the interest is paid every single month. And the advantage of having something compounded frequently is it allows us to earn interest on our interest. That's what compound interest is. How much interest will be earned after 5 years? So here's my formula. We know the initial amount, that's the 5,000. So P is 5,000. We're given the interest rate, that's 6%. I'm going to write that as a decimal. 6%, move the decimal 2 places to the left, I get 0.06. Compounded monthly means we have 12 payments per year, so n is 12. And we want to know what's going to happen after 5 years, so t is 5. So I'm going to go ahead and plug those numbers into my formula. A equals 5,000 times 1 plus 0.06 divided by 12 to the 12 times 5. 12 times 5 is 60, so I'll go ahead and make that exponent 60. To do this computation, I'm going to need a calculator, so I'm just going to put this into a calculator. And if you need help figuring out how to enter this into a calculator, please let me know. I'm not going to show that here because every calculator is just a little bit different. But I put this into a calculator and got $6,744.25. Now that's not actually my final answer because they're asking me how much interest will I have earned. And this 6,000 figure is the future value of my account. I started with $5,000. It grew to this $6,700. And so the amount it grew by is interest that I've earned. So I can take that future value number, I can subtract my initial value, and I get an increase of $1,744.25. And that increase is my interest. So this $1,700 number is the interest that I've earned. Now in the previous example, we looked at a situation where our interest was being paid out every month or once a month. In many situations, we might have growth that happens continuously, all the time, rather than just once a month or once a year. And our formula changes when we talk about continuous growth or decay. It changes to the following: A of t equals P times e to the RT. P is still going to be our initial value or our principal. R is still our interest rate or growth rate. And T is still time. If you were given an annual growth rate, T would be time in years. If the R is bigger than 0, we're talking about exponential growth. And if the R is negative, then we'll be talking about exponential decay. This E right here is a number. It's an irrational number, just like pi. A lot of calculators have an E button on them. E is referred to as the natural number, and it's approximately 2.7, but it has a decimal that continues forever, can't be written as a fraction. It's an irrational number. So let's take a look at an example. A scientist begins with 100 milligrams of a radioactive substance that decays continuously. So this is continuous decay at a rate of 16% per hour. How much will be left after 1 day? So because it says decays continuously, I have to use this formula with the E. A equals P, e to the RT. The P is the initial value, and in this case, we're starting with 100 milligrams. R is my rate, and because it's decaying, I'm going to make it negative. 16%, written as a decimal, is 0.16, and again, I make it negative because it's decaying. Because this rate is given per hour, that means T has to be measured in hours. So we want to know how much is left after 1 day. So that means for the T, I'm going to plug in 24. So I've got 100 e to the negative 0.16 t, and then I'm going to put 24 hours in for t. And once again, this is something that I have to do with a calculator. I put it into my calculator and got approximately 2.15 grams. I'm happy to help anyone in class or outside of class if you want to see how to do this in a calculator. All right, so earlier I mentioned that we have exponential growth if our base is bigger than 1, exponential decay if our base is smaller than 1. So let's compute tables of values for f of x equals 2 to the x and f of x equals 1/2 to the x. And then we're actually going to graph both of these functions and make some generalizations about the graphs of exponential functions. So 2 to the x, I'll start with that one. If I plug -2 in for x, I get 2 to the -2, negative exponent, so I move it to the bottom. That's 1/2 squared, or 1/4. 2 to the -1 is 1/2 to the 1, or 1/2. 2 to the 0 is 1. Anything to the 0 power is 1. 2 to the 1 is 2, and 2 squared is 4. Notice that the y values are always doubling. 2 to the x means your y values double. All right, what about 1/2 to the x? If I plug in -2, 1/2 to the -2, negative exponents mean reciprocals, so I can flip it and make the exponent positive. I get 2 to the 1 squared, that's 4. 1/2 to the -1, flip it, make the exponent positive. 2 to the 1 is 2. 1/2 to the 0 is 1. Anything to the 0 power is 1. 1/2 to the 1 is 1/2, and 1/2 squared is 1/4. In this case, our base is 1/2, and the y values are being cut in half. So the table of values on the left are increasing, exponential growth. The y values on the right are decreasing, exponential decay. So now let's actually graph both of these functions and talk about some features of the graph of exponential functions. So I'm going to start by graphing 2 to the x, and so I'm just going to be graphing the points from this table of values. So when x was -2, y was 1/4, -1/2, 0, 1, 1, 2, 2, 4. And there's the graph of y equals 2 to the x. Notice that's an increasing function because it's exponential growth. Now if I graph the points I got for g of x equals 1/2 to the x, I had -2 went with 4, -1 went with 2, 0, 1, 1/2, 2 1/4. Here's my exponential decay, my decreasing function. So these graphs actually look pretty similar, other than one's increasing and one's decreasing. In fact, they both have the same y-intercept at 0, 1, and they both have a horizontal asymptote at y equals 0. Just 2 to the x has that horizontal asymptote on the left. 1/2 to the x has the horizontal asymptote on the right. So let's just make a list of some of these characteristics. If you have an exponential function of the form f of x equals b to the x, so the a is 1, the domain is all real numbers. You can plug anything into an exponential function. We're allowed to have any kind of numbers for exponents, positive, negative, but the range is going to be 0 to infinity. If you look at these pictures, the outputs are always positive. And not including 0, because we have this asymptote. It's approaching y equals 0, but never actually reaching it. So asymptote at y equals 0. We're going to have an intercept of 0, 1. If that base is smaller than 1, we have exponential decay. That means the function is decreasing. And if the base is bigger than 1, we have exponential growth, and that means the function is increasing. So let's do another one. Let's graph f of x equals 4 to the x. State the intercept, asymptote, domain, and range. So for this function, the intercept is going to be 0, 1. The intercept of these exponential functions is always at 0, 1. If I don't remember that, just plug 0 in for x. 4 to the 0 is 1. because my base is 4, it's exponential growth, it's increasing. And the bigger the base, the more steep the graph is, the more rapidly the increase is. And so an easy way to illustrate that is if I plug in 1 for x, I get y equals 4. So this graph is going to go through the point 1, 4. I can see on the graph that my domain is all real numbers. That's true for all exponential functions. My range is 0 to infinity, not including the 0. I have an asymptote of y equals 0 and an intercept at 0, 1. Now, we can also use graphing transformations to graph modified versions of these exponential functions. So, for example, if I want to graph f of x equals 2 to the x plus 1, I know what y equals 2 to the x is. We graphed that earlier. So we can think of this as a parent function of y equals 2 to the x, and then this plus 1 is a graphing transformation that's happening inside the exponent. So it's an input transformation that's going to impact our x values. We do the opposite of what it says. It says plus 1, so we're actually going to move the graph left 1 unit. So we graphed y equals 2 to the x earlier, has a y-intercept of 1, and it went through the point 1, 2. So in red, there's the graph of y equals 2 to the x. And so I can take these points and shift them left 1 unit. So the point that was the y-intercept goes left 1 unit. It's at negative 1, 1. The point 1, 2 goes left 1 unit. That's now my new y-intercept at 2. And there's the graph of, in blue, f of x equals 2 to the x plus 1. Here's another one. Let's do negative 2 to the x plus 3. So we can start with that same parent function, y equals 2 to the x. Y equals 2 to the x has a y-intercept at 1 and goes through the point 1, 2. This negative is outside of the exponent. It's an output transformation. It's going to impact the y values. We're going to take the y values and make them negative. That's going to reflect the graph over the x-axis. The plus 3 is outside of the exponent. It's an output function, or output transformation. It also impacts the y values. So we're going to be shifting it up 3. So I'll do my reflection first. I take this graph in red and I just flip it over the x-axis. That makes all those y values negative. So the y-intercept, which was at 0, 1, is now at 0, negative 1. The point 1, 2 is now at 1, negative 2. And then finally, I'm going to take this reflected graph and I'm going to move it up 3 units. So my y-intercept goes up 1, 2, 3 units. It's now at 0, 2. This point, 1, negative 2 goes up 1, 2, 3 units. And that asymptote also went up 3 units. So originally we had an asymptote at y equals 0. It went up 3 units. It's now at y equals 3. All right, that was my last example. Please let me know if anything in this video is unclear.